Mathematics. Today we are on problem number 28 of the 2024 Universal Florida Integration Bee qualifying exams, and we'll be looking at the definite integral from x equals to 0 to x to positive infinity of the natural logarithm of x over 1 plus x to the power 4. So this is a very interesting problem, and today the focus really is not in solving this problem, but in connecting a series to a constant. We'd like to see how we can connect this series that is interesting to a specific constant. But yeah, without much ado, we'll move forward to the solution phase of this problem. And before we even step there, I'd like to encourage those of us here who are here for the first or second time and haven't subscribed, or even if you've been here for a number of times but haven't subscribed, we encourage you to consider subscribing to our channel. Your support will go a long way in increasing the profile of this channel. So without much ado, we are moving forward to that solution phase. So this is our problem, right? The definite integral from x equals to 0 to infinity of the natural logarithm of x over 1 plus x to the fourth. So my point of interest is around this natural logarithm in the numerator. And imagine you had a function y is equals to x to the a, right? And I want to differentiate y with respect to a. What do I do? So the first thing I would do is I would take the natural logarithm of y, and this is the same as a times the natural logarithm of x. Okay, why? Because I used the rules of logarithms that tells me that if I have a natural logarithm of a to the b, that's the same as b times the natural logarithm of a. So this is what I used, right? Such that 1 over y dy dA is equals to that, and therefore dy dA is equals to y natural logarithm of x, which is equal to y here is x to the a, so we have x to the a natural logarithm of x. So this is an important thing. Why? Because if I considered a to be 0 here, then I am back here. In other words, if we created an integral I to the a, which is equals to the integral from 0 to infinity of x to the a over 1 plus x to the fourth, then the derivative with respect to a will be obviously, and here we are invoking the differentiation under the integral sign, which is equals to right, and therefore what this means is that our original integral is the same as the derivative of the integral IA, where IA is 0, which is equals to Okay, so what does that tell us? It tells us that if we solve for this, then we can differentiate whatever we get, and that will lead us to this by substituting a with 0. Okay, so that's where we've gotten. Okay, so IA is our integral from 0 to infinity x to the a 1 plus x to the 4th dx. But there's this very special integral that comes from Euler's reflexive relation, where if we have being equal to m over 1 plus x to the n, this is equal to 1 over n pi over sine of pi m plus 1 over n. Okay, and I will leave a link in the description if you are really interested in knowing how this relationship comes by. But this is a known relation. So we had forgotten to indicate that obviously in this relation m is less than n, and so up here a is going to be less than a 4. So in other words, I of a, using this box to relation here, is going to be equal to 1 over n in this situation is 4, so 1 over 4 times pi over the sine of pi a plus 1 divided by 4. Okay, so we have come to a point where we found that I of a is a quarter pi over the sine of pi times a plus 1 over 4. And what's the derivative of I of a? This is the same as a quarter times pi times could even be a definite a full differential. It doesn't have to be partial, but I think it's still okay here. So this is a quarter times pi times negative of obviously pi over 4 cosine of pi over 4 a plus 1 times sine squared pi over 4 a plus 1, which is negative pi squared over 16 times cos of pi over 4 a plus 1 over sine squared pi over 4 a plus 1. So we're going to now substitute 0 for a, and that means that is the same as negative pi squared over 16 rather, times cos rather pi over 4 over sine squared of pi over 4. This is pi squared over 16 times root 2 over 2 times root 2 over 2 times root 2 over 2. That goes. So we have negative pi over 16 times, focusing on that, 2 over root 2, 8, and this is negative pi squared over 8 root 2. So that is good. So for a minute we have our solution being equal to negative pi squared over 8 root 2. But so that's the first step. Now let's go and look at the series that I talked about. We have IA being equal to 0 to infinity of x to the a over 1 plus x to the fourth. Okay, which is the same as 0 to 1 x to the a 1 plus x to the fourth plus 1 to infinity xa. Okay, so this is good. We have the reason I'm trying to do this, I'm going to try and use power series, and that's why I'm laboring to. So let's focus on that part for a minute, and let me just highlight it. We're going to focus on this bit for a minute. So we have 1 to infinity x to the a over 1 plus x to the fourth, and this is the same as 1 to infinity 1 over x negative to the power negative a, and then we have 1 over x the fourth plus 1, and then we have dx over x to the fourth. And so we can say let u be equal to 1 over x, meaning that du dx is equals to negative 1 over x squared. And so du, negative du can be used to substitute for dx over, x squared. So let's just delete that and have it written properly. And we see when x is 1, it's going to be, u is going to be 1. When x tends to infinity, u is going to tend to 0. And so 1 to infinity 1 over x negative a 1 over x plus 1, we have 1 over x squared, we have dx over x squared, which means that this is the same as 1 0, we would have u negative a over u to the power 4 plus 1 times this here is u squared, so we have u squared, and then we have negative du. So this negative sign here allows us to flip the sign. So we have 0, 1, then we're going to u 2 minus a over 1 plus u to the fourth du. So what does this tell us? It tells us that our original integral to infinity of x to the a over 1 plus the fourth is the same as 0 to 1 x to the a 1 plus x to the fourth plus let's not use u but rather use x there. So we have x 2 to the a over 1 plus x to the fourth, and one thing we know is that in this domain the absolute value of x is less than 1, and using geometric progression, we know that when you're summing from k equals to 0 to infinity of x to the k, that's the same as 1 over x. Similarly, if you have is the same as 1 plus that. So using these relations here, we can say that our integral 0 to infinity of x to the a over 1 plus x to the 4 is the same as 0 to 1 x to the a summation from k equals to 0 to infinity of negative 1 to the k x to the power 4k plus integral 0 to 1 x to the power 2 minus a summation from k equals to 0 to infinity of negative 1 to the k, and then we have x to the power 4k, right, dx. And so we can flip the summation sign and the integration side without losing any generality. So we have k from 0 to infinity, negative 1k, integrate 0 to 1 x to the power 4k, 4k rather, plus a. And then plus k is equals to 0, infinity, negative 1k, integrate from 0 to 1 x to the power 4k plus 2 minus a. And we could even combine things up so that our integral is 0 to infinity, negative 1k, summation, integral from 0 to 1, x 4k plus a, plus x 4k plus 2 minus a. So which is x 4k plus a plus 1 over 4k plus a plus 1, 0, 1. And we have 1 over 4k plus, we're adding 1 to 3, so this becomes 3 minus a. There's x here rather, so 4k plus 3 minus a, 0, 1. So this is 0, infinity, negative 1 to the k, and we have 1 over 4k plus a plus 1 plus 1 over 4k plus 3 minus a. Okay, so we're making quite significant progress here. So we've come to IA is equals to the summation from k equals to 0 to infinity of negative 1 to the k, and let's just use that kind of bracket, 1 over 4k plus a plus 1 plus 1 over 4k plus 3 minus a. Now, to differentiate that with respect to a, we get we have negative 1 over 4k plus a plus 1 squared plus, because this minus here is there, it cancels the minus, so we have plus 1 over 4k plus 3 minus a squared. Now, that same with a equals to 0 means that we have the summation, and let's begin, because this goes to 0, this goes to 0, so we have 1 over 4k plus 3 squared minus 1 over 4k plus 1 squared, and there's a k here. So what we have seen is that this series is equal to what we showed previously. We have shown that this is equals to the summation from k equals to 0 to infinity, negative 1 to the power k of 1 over 4k plus 3 squared minus 1 over 4k plus 1 squared. This is equals to negative pi squared over 8 root 2. Therefore, the integral 0 to infinity, the natural logarithm of x over 1 plus x to the power 4th, is equals to the summation from k equals to 0 to infinity, negative 1 to the k, 1 over 4k plus 3 squared minus 1 over 4k plus 1 squared, which is equals to negative pi squared over 8 root 2. So this is what we wanted to show all along. It's an interesting relationship, and yeah, I think it will be hard to try and show it just by having the series to begin with, and vice versa. But it's a nice relationship all the same. I hope you've learned a thing or two. If you have any question, please don't hesitate to reach out to us. We'd be very, very much willing to hear from you and learn from you as well. So until next time, have a wonderful, wonderful day ahead, and be blessed.